Welcome to the 28th lecture for Physics 4B. We are beginning to wrap up our semester in this lecture, fully unifying electricity and magnetism in one united theory of electromagnetism. We start with a lecture video we skipped when we covered the Faraday's law a couple weeks ago to help us appreciate the similarities that are developing between the magnetic and the electric fields. In fact, when we covered the Faraday's law is when we started to refer to the four equations that we will call Maxwell's equations. We review them here and the story each equation tells. After this review, we are prepared to reenact the scenario considered by James Clerk Maxwell to come up with the Maxwell term in the Ampere's law. And the reason this set of four equations are called Maxwell's equations. With the full set of Maxwell's equations, we will derive the wave equation of electric and magnetic fields in the next lecture. And for now, for this lecture, we go over some mathematical preliminaries.
So let me start by noting some things that you will see in the chapter. So I will start out with the chapter 13, knowing I'll go back to chapter 12 for some materials. So let me just go into section 13.4, induced electric fields. There's really one expression that I want to write down from here, which is this. This is Faraday's law. This is the standard way it's written and presented. Faraday's law says that this line integral here, it's a line integral of electric field along a path, and this loop thing says that that path is a closed loop. That line integral is given by change in the magnetic flux. So it's equal to rate of change of magnetic flux, but there's a minus sign there. And in the lecture, we go into what the minus sign means and how that's related to Lenz's law. So that's what Faraday's law says. And in the most context of this class, we just focus on the fact that this quantity here, it gives you induced voltage. And most of the time, we just want the voltage that gives us what we want. So we just work with that. We don't really try to find the electric field. So, okay. Now, what I wanted to do was I wanted to compare this to a situation where we do try to find the thing inside the integral. And I want to show this to you side by side so that you can see a remarkable similarity between Faraday's law and Ampere's law. Let me get to Ampere's law. So that's Ampere's law. Let me copy it over. And you can see how similar Ampere's law and Faraday's law are in terms of mathematical form. So Ampere's law says that this line integral, dot product between magnetic field and some path, and the path is around a closed loop, that quantity is given by current. Let me use the constant that I'm trying to use more. So you can rewrite this mu naught as 4 pi times Coulomb constant over c squared. So that's how I'm going to write it. 4 pi Coulomb constant over c squared times the current enclosed. And if you forget the physics for a minute, then there's a great deal of so the reason I say forget the physics for a minute is because in terms of physical interpretation, there is a distinction and difference. So in terms of physical interpretation, when you look at this E dot dl, that has a very clear interpretation. That's voltage. That's the definition of voltage. When you look at B dot dl, line integral of magnetic field along the path, that doesn't have any physical meaning. Like the quantity means nothing because that's not related to work. The way magnetic force works is different, and so when you're looking at the physical quantity itself, you don't really see the similarity between these two expressions. And it's also harder to see similarity between current enclosed and the rate of change of magnetic flux. So that's what I mean if you forget the physics for a minute. If you ignore the physical meaning assigned to these symbols, so if you just look at the algebra, if you just look at the mathematical expressions, this is, I hope you see the similarity. You have, so both of these magnetic field and electric field, they are examples of what's called a vector field. So thinking of both of these quantities as vector field, again, forgetting their physical meaning for a minute, what you have here is a dot product of a vector field with a path, dot product with a vector field with a path, and you take the path along a closed loop, then you have this integral of the vector field equaling some constant value on the right hand side. So that similarity in mathematical form, it gives you something. You can get some things out of that, and I will show that to you in a minute. As we get into that, I want to bring back the physical meaning here. Better description might be the conceptual meaning here, because sometimes it's very easy to get lost in fancy mathematical expressions and forget conceptually what these expressions mean. So this is what these expressions mean, and this is the way I like to kind of present. So these are two of the four Maxwell's equations, and I like to talk about Maxwell's equations even in Physics 10, but with the people who haven't taken calculus, I still like to describe these expressions in terms of using English language, in terms of plain phrase that still has a meaning that's not wrong. So this is how you can describe it in those conceptual terms. You can say, so this is Ampere's law, and if I describe the Ampere's law this way, it would be imprecise. It's not as precise as mathematical expression would be, and within the limitation of imprecision, it's as correct as it can be. So this is what I would say. Ampere's law says magnetic field is produced by electric current or by current. Or you can turn it around, put it another way. Current is source of magnetic field. This is how I mean it. The terms you see on the right-hand side here, this is what you could call source term. In a conceptual sense, this is what produces the things on the left-hand side. So if my current here were 0, then it's very easy to make the left-hand side 0 by making magnetic field 0. I mean, it doesn't mean that it has to be, but for this quantity to be non-zero, somewhere current has to be non-zero. So when you read this calculus expression, this expression here is what says the current is the source of magnetic field. And the upside of describing this Ampere's law expression that way is you can say something similar, something very similar about the induced electric field as well. So what Faraday's law says is, okay, so we have electric field. Okay, let me just write that down for now. Electric field is, and your textbook will draw a distinction between induced electric field and electrostatic electric field. And there is a real distinction there, and I'll talk about that in a couple minutes. So I can say electric field is produced by, and what is it produced by? I guess this really takes some math to describe what it is. So again, this is what I would call source term. So if this source term is 0, it's very easy to make the induced electric field 0. And the way this wouldn't be zero is if the magnetic flux had a non-zero rate of change. So let me say electric field is produced by, um, let me just say change of magnetic flux. Change of magnetic flux is the source of the electric field that's shown on the left. The change in magnetic flux is the source of induced electric field. And with the conceptual description, what this similarity in the mathematical form means is there are things that you might have noticed when you are dealing with the magnetic fields. Those are directly applicable to whenever you are dealing with induced electric field. Here's the biggest thing. This is one of the things that your textbook says at the top of this section. It gives you something about a property of a magnetic field. It says that a fundamental property of static magnetic field is that unlike an electrostatic field, it is not conservative. And they are absolutely right. Magnetic field is not a conservative field. Now, what they say a little bit later is not quite right. Okay, so this is not quite right. A conservative field is the one that does the same amount of work on a particle moving between two different points, regardless of the path chosen. What they should really say is that a conservative vector field, as in, we are talking about a mathematical quantity. We are not talking about the force and work. So we are in the realm of math. And conservative vector field is defined as one where the line integral, like this integral here, is path independent. So they chose to describe this integral as amount of work. And that is true for electric field. But for magnetic field, because the magnetic force is really weird, this line integral, it doesn't correspond to the work done by a magnetic field. But so with the caveat, what they say here is absolutely right, that the property of magnetic field as a vector field is that it's not conservative. And that has a very, very specific mathematical meaning that I want to point out. And that the mathematical meaning, it can be shown visually. And that's what's really striking about these properties. And I think the best way to show this is on the Wikipedia page for vector fields, which I hope touches on the topics you cover in multivariable calculus. And I should give you full disclosure, which is I've never taken multivariable calculus. When I was undergrad, they let me take upper division electrodynamics instead of vector calculus, multivariable calculus. So I never went back and actually took it, but I do know what I need to know to be able to do physics. And yeah, so that's the full disclosure. But what I will tell you is that I think the reason the math department at UC Berkeley accepted my upper division electrodynamics coursework as a replacement for the lower division multivariable calculus requirement is that there's a lot of overlap. When you're doing electrodynamics, particularly at upper division level, there's a lot of multivariable calculus stuff that you just have to learn. And some of those things we are basically skipping over. Most of the semester, we are presenting this integral form of the Maxwell's equations. And at the very end of the semester, I will show you the differential form and talk about the differential form a little bit. And let me write down one more expression, which I think will draw a good contrast to these two expressions. Let me clean up the space a little bit here and write down the one other equation that looks kind of like Ampere's law and Faraday's law, but it's actually very different. And that different form is tied to different aspects or properties of vector field that it describes. Let me write down Gauss's law. That's the thing that looks kind of like Ampere's and Faraday's law, but when you look into it more carefully, that it looks rather different. So Gauss's law says that this integral, it's over some closed geometrical object, but that geometrical object is not a line, but it's an area. Gauss's law says that this quantity is equal to 4 pi Coulomb constant times the amount of charge enclosed. And if you look at this expression carefully, you can assign meaning or you can give it a conceptual description, similar way I've given to Ampere's and Faraday's law. You can say that this type of electric field is produced by static electric charge or by electric charge. You can say that electric charge is a source of this type of electric field. And even though these two expressions look very similar, there is a distinction between them. Here, the integral is the one-dimensional integral around the closed loop. Here, it's a two-dimensional integral over a closed surface. And that distinction becomes more manifest if you look at the differential form. The differential form of Gauss's law looks like this, the divergence of the electric field, the vector field, is equal to 4 pi Coulomb constant times the charge density. And the differential form of Faraday's law says the curl of the electric field is equal to minus rate of change of the magnetic field. So when you write down the differential form, then the mathematical difference between the two becomes much more clear. Here, I'll just have to ask you to watch out for that key subtle difference between the area integral and the line integral. And this is the property of a vector field that each of these forms of expression relates to. So let me scroll down. When I was looking at this page a little bit before the virtual class session, I saw vector field that where I can tell you is indicative of a vector field that's produced by source of this form. So this page has a kind of a general, more generic vector field here with something like this. In a kind of general vector field like this, if someone were to ask, how does what's in here relate to quantity like this, or how does what's in here relates to quantity like this? Here it's not very all that clear. This is a kind of an arbitrary vector field. It can be anything. But this page shows two very distinct types of a vector field that is clearly related to one or the other mathematical features. So this one relates to the divergence, and this one relates to the curl. So let me show you those vector fields. The first, this one shows a vector field that has to have divergence. Now, this is still somewhat arbitrary looking vector field, so it's not necessarily electric field. It's it could be something different. But when you look at this set of arrows, they have a kind of distinct feature in that all these arrows seem to be pointing into one location. Or if you reverse the direction, then it would be these arrows appear to point away from that point. And if you kind of imagine a three-dimensional version of that, where in 3 dimensions you have these arrows pointing towards a point, then that's the kind of a vector field that is associated with this. Because you can imagine defining a kind of a surface, and the dot product of the vector and the surface area element will on net point in the same ish direction. So when you calculate this, the flux of the vector field, you'd get some non-zero quantity. And in electrostatics that relates to the amount of charge enclosed. So this is an example of a vector field where this integral over some surface that you define that includes this point would be non-zero. But if you imagine calculating something like this, something like a dot product over, or some kind of a path integral over a path, then this is a kind of vector field that would result in a zero for that when you look at it. So let me just draw a path to help visualize. Imagine you have a path that looks like that. And I guess with this particular one, you could arrange it so that maybe it is not zero. But this is kind of what I'm looking at. So if we are looking at this path or this path here, the vectors are kind of perpendicular. So the line integral here would give you zero line integral. Now, along this path, these vectors is where if you did E dot dl, you'd get positive line integral. But along this path, you are going opposite to the direction of the vector field. So you can imagine that if you calculate E dot dl here, this would be negative. And for fields that are, say, produced by static charges, like here, then these integrals always work out so that they are zero. And this is really what leads people to say that electric field is a conservative field. So that's the vector field description of what matches to what we discussed under Gauss's law. Now, what we talk about in Faraday's law, and technically what we did talk about in Ampere's law, is another type of vector field that looks very different from what you see with Gauss's law, what you see with the static electric field. And it looks like this. This is an example of a vector field that this kind of vortex-looking vector field is one where if you imagine doing a calculation like this one, the line integral around the closed loop, then you can see that as you go in a closed loop, making sure to contain this point, that the direction of the line and the direction of the field goes in the same direction. And for it to be like this, there has to be something that kind of looks like a vortex. And when you have that, you get a vector field that looks like an induced electric field and actually also looks like a magnetic field that's produced by current. And when you see a vector field like that, there should be some kind of a source here. And for us, that source, for us in the context of magnetism, that source is current. So if you had a current that's coming out of the screen at that point I marked, then you would have a magnetic field that's going around in the direction indicated there. So that's the magnetic field description. And what this mathematical similarity means is you can imagine an analogy that can help you get a hold on how induced electric fields are generated and what they look like. So I described this source as a current. That's the case of Ampere's law. I can imagine describing it as current. Or I can imagine this as a region containing magnetic field. And that magnetic field is going to be changing in value so that this magnetic flux is changing over time. So this source can also easily be the rate of change of magnetic flux. And if I have that arrangement here, that I can imagine like a solenoid that's producing a magnetic field, and the amount of current in the solenoid can be changing in such a way that it produces this change of flux over that area. And what Faraday's law tells me is that that will induce electric field that goes around that source of the induced electric field. And in purely mathematical terms, that'll look a lot like magnetic field due to a line of current. And so I want you to draw that comparison. and that there's a great deal of intuition you can gain about the induced electric field by thinking of it as being somehow a bit similar to magnetic field. And that way of looking at it justifies some of the things that they say in the section 13.4, induced electric field. They say this, specifically, the induced electric field is non-conservative because it does a network in moving a charge over a closed path. And yeah, it's a in terms of a vector field, it's a non-conservative field because when you have vector field that looks like this, then this is not a conservative field. And actually that ties to what they're saying here, that it cannot be written as a gradient of a function because the function whose gradient this could be written as, that function would be the scalar potential that you can attach to a conservative field. And because in the case of electric field, the direction of electric field is the direction of force, this sense of non-conservative, it applies as a vector field, and it also applies as a force. The force due to an induced electric field is non-conservative. And what I want to assure you of is energy conservation on the whole is still valid, because in producing this induced electric field, which is non-conservative, there has to be a change of magnetic field. So that would mean change of current, and there's enough complexity there. You can figure out where the energy is coming from and where the energy is going. So I'll just leave that there, but I think drawing that analogy between the electric field produced through Faraday's law and magnetic field produced through Ampere's law, that analogy will help you gain understanding of things like what they're saying here, what it means for why induced electric field is non-conservative, and the mathematical features of this.
All right, so what I want to talk about is what we have been covering so far. In fact, you've seen me write down this set of equations a little bit mid-semester as we were about to introduce Faraday's law. So let me write them down again as a reminder. So let me write them down first, and then I'll write down their names. The one regarding the electric field, E dot dA, is integrated over a closed surface, is the amount of charge enclosed over epsilon naught. And we talked about an analogous version for magnetic field, that if you try to compute this quantity, except for magnetic field, that you get 0. So this is a magnetic flux integrated over a closed surface, that it's always equal to 0. Does anyone remember why it was equal to 0? So in the context of magnetic field, intuitively, why would you say this makes sense? That without having to do any calculation, you can say, well, the net amount adds up to 0. Like what property of magnetic field? Not about change, but what can you point to something about magnetic field that's different from electric field, that you can say, no matter how you set up the surface, it's always going to add up to 0. Kevin?
Just say magnetic field always has the same amount of outlets.
So, right, that's what you see with the features. So let me, yeah, so I want people to be able to explain that. So that's something that you are used to seeing with the magnetic field. So let me draw the common magnetic field lines that you might have seen, and that's what you might be imagining. Like a field lines that go like this. That's the most common one that you would have seen with magnetic field. And so if you simply looked at it, you would say, oh, this is a magnetic field due to a due to a bar magnet with the north and south pole. And here, the feature you see is that when you now imagine a surface that's enclosing the magnet, for every field line that goes out, there's a field line that comes in. Why? I mean, so that is a feature you see. What more fundamental thing could you point to and say, this explains the feature that you are seeing? Do you know? This is the one thing that magnetism is different from electricity.
You couldn't just as a property of the magnet, right?
We could use that as a starting point. Tell me property of magnet.
Yeah. Okay. Yeah, I just remember like all magnets, every time you like massive equal amount of magnetic fields going in and out.
Right? So, I mean, it's another way to put it is, this is a different ways of stating the same thing. And that's a way of, that's a measure of how well you understand something. If you can state something in one way and one way alone, then you have memorized it, which is, better than not knowing anything, but you haven't really understood it. When you understood it, then you can express it in multiple different ways. So you might have just from, I guess, matter of knowing basic science effect, you might know that magnet always has same number of field lines going out as coming in. And a different way of stating the same thing is that the magnet always has north and south pole. That you never have north pole by itself or south pole by itself. If you split this in half, so trying to separate north and south pole, you do get just the north and south with the smaller magnets. So that's the basic feature of magnetism, that you never see a single pole by itself. So this is how I want you to think about every equation you see in physics and actually even engineering. Every equation has a story to tell. Gauss's law for electric field says that this is a way of counting how many charges are enclosed within a surface, the way you saw with the electric field lines. And what this is saying, you could say that this is saying the same thing. The magnetic, this quantity, calculating this is a way of counting how many magnetic monopoles are enclosed within the surface. And with the magnetic field, it just says, well, you can do that and you will get 0. Because so far, despite numerous search efforts, people have found no magnetic monopoles. So you could go one step further and say that what this statement means is there are no magnetic monopoles. And I guess with this statement, we kind of have to just stop here. We don't really have an explanation of why are there no magnetic monopoles. In fact, in terms of theoretical physics, it would be nice if there was some magnetic monopoles, maybe just one. And so people are looking for it, but the experimental fact is that no one has found it in a way that people could replicate it. There have been 1 or 2 cases where people thought they found it, but they tried to replicate the experiment in a larger scale and they couldn't. But so until somebody finds a magnetic monopole, this is the version we'll go with. When somebody eventually finds it, we'll say, it's the magnetic charge enclosed times mu naught. But until then, we'll just leave it in this form. So these two you have seen so far. And so the subject of your exam 3 was what I'll write down now. Ampere's law and Faraday's law. So Ampere's law says that it deals with this magnetic field. It says that instead of calculating the flux, you calculate a line integral, B dot dl. And you are calculating this integral around the loop. Now, normally you wouldn't do this with the electric field because the type of electric field you have seen in static electricity, if you did this, you would get 0. So you wouldn't do that. But with the magnetic field, when you do it and do it around the closed loop, then you get, then this is equal to mu naught times I enclosed. And we spent a fair amount of time talking about what it means for current to be enclosed. Do you remember? So let me draw this as an example. Suppose I have a current that's going from left to right. So it's just an infinite long line of current, I. How would I choose a loop that would be basis of this integral here? How would I choose a loop that somehow encloses this current? Circle around it, okay. So you mean the Amperian loop that you will pick would look like this, right? So in what sense does this loop enclose this long line of current? So this is correct, but can you explain why, in what sense this encloses it? I mean, but it doesn't enclose in the traditional sense, right? Like if I talk about enclosing a charge, that's easy to imagine. Charge is one-dimensional, or it is actually a three-dimensional object. It occupies some volume, and I put that thing that occupies a volume within another volume. Then I say that's enclosed. And you can see that without going through any of the surfaces here, it can get out. So we say that's what it means to enclose a charge. So that's why we didn't bother going through this detail with the Gauss's law. It's intuitively clear what it means for a charge to be enclosed. But with the current, we had to be more mathematical, more formal. Because here, I mean, the current, it comes in from very far away from this loop. And it also moves out to very far away from the loop. So we want to be more precise about what it means for this current to be enclosed. It's not enclosed in the sense that it's confined within this loop. So it's been a while since we talked about it, so you might have forgotten. Anybody remember how I try to make more precise what it means for current to be enclosed inside the loop? So going through loop is it's a step in the right direction. So you mean if I have a loop, we say if it's going through the loop, it's enclosed. If it's not going through the loop, then it's not enclosed, right? But what does it mean for? I want to make it mathematically clear. What does it mean for this current to go through a loop? Imagine something like this. If I had a current that's going like this. So imagine this is a wire that my current is flowing in. If my current is going like this, is it going through the loop? So current comes in, bends around, and comes back out. Do you want to consider that as going through the loop? Not really, right? So however we define the current, we want to be able to say that something like this, it doesn't really go through the loop, but something like this, where it goes through and goes out to infinity, actually goes through the loop. What about something that's going around like this? Would you say this goes through the loop? Right? It goes through inside one way, and then the other time as it's coming around, it's actually not going through, so it doesn't cancel out this time. So we want to have a mathematically precise definition of what it means for this line to go through a loop so that we can actually count, we can actually calculate. Do people remember how we did that? It's a geometry question. So it's the sort of similar conceptual exercise as what we did when we were defining right-hand rule. I mean, I could have given that right-hand rule to you to simply memorize it by rote, but that's something you would forget right after this class. I didn't want to go that way. So I want to make sure we spend the right amount of time on this as well. I can just give you the rule, just something to memorize by rote, and you'll forget it right after this class, and it won't do you any good. So the way we defined the right-hand rule was we were trying to come up with a quantity that had a direction, that was associated with two quantities that has direction. I mean, when we were introducing right-hand rule, cross product, you already knew about dot product. So you knew how to multiply two vectors in a way that they give you a scalar. But we are trying to define a quantity that has direction. So what we started out with was, well, if you have two vectors, what kind of geometric quantity does this can this define? And we said it can define a plane. Right? And then everything else starts from that. You try to associate a vector with a plane, and so that's a normal vector, and you try to come up with a sense of direction for that. That's where right-hand rule actually comes in. So with this, we can start a similar line of inquiry, as in I have a loop. So it's a question of what other associated geometrical object can a loop help me define? So a loop is a one-dimensional linear object. Chris, you had an idea for what a loop can define?
A plane also?
Yeah, loop can define a
surface or an area?
surface. I want to be more general than a plane because a loop can be something crazy like this. Like something like this. This is a loop. It doesn't quite define a plane, but it can define what's called an open surface. It can define a surface that's bounded by this loop. So this loop, for example, can define this circular open surface that has a that has the loop as its boundary. Good? And then what we can say is, well, what it means for the current to go through the loop is that it goes through this surface. So each time the line pokes through the surface, we count it as being enclosed. So you see that rules out this as being enclosed in a net sense, because it pokes through once and then it pokes back out the other way, so those two cancel out. Whereas this one, it pokes through one way, but as it comes around, it doesn't poke through again, so it counts only one way. So, and I think the next level of discussion is which we kind of skipped the first time we saw it because, we're going to come back to this. So this is the question. Is this circular surface the only surface this loop can define? Or are there other surfaces that this circular loop can also define that's not this circle? Right? Imagine this circle as being made out of rubber, so you just start stretching it. And the example I did during lecture was with a balloon, right? This opening is the loop, and as I put more air in it, the surface stretches, but it's still bounded by the same opening. So here you could imagine this green area being bounded by the loop, or you could imagine something like this being bounded by the loop. Some kind of cylindrical area that first stretches out this way, and then has opening here, and then stretches out this way. Right? So there's actually what seems to be an ambiguity, as in as this current comes in. So we are trying to say, in trying to define precisely what it means for current to go through, we want to say, well, the moment it goes through this surface is when it's enclosed. But it seems like if we choose this blue surface area instead of this green surface area, then the current actually pokes through here instead of not here.
So everyone sees the ambiguity here. Ambiguity in choosing different surface, sort of surface that's defined by the loop, same loop. So the question here is then, does this ambiguity matter? As in, can you come up with a situation where using this surface, you would say a current is enclosed, but using this surface, you would say current is not enclosed. So let's think through a couple examples. So the example that's drawn on the board, it doesn't actually matter which surface you pick, right? The current still pokes through each of these ones. What about this example that I was looking at, where current comes in, turns around, then goes back out? If you choose the circle as your surface, then is your net current 0? Still 0, right? What if you pick something like if you pick the cylindrical surface with this end being closed, it's still 0, right? Okay, let me try changing the circumstance a little bit. So if I pick this one where the current goes through and then loops around like this, then you have non-zero net current going through. All right, this gives me an idea. What if I do something like this? Like current bends like this. In this case, the net current going through this surface, that's 0, right? It never actually pokes through. What about the net current through this cylindrical area? Think through carefully. So there's a positive coming in through this surface, and then what happens? Yeah, it has to leave through the side, right? So it turns out, so in this case, it's 0. And it turns out, no matter what kind of example you can think of, the current that comes in has to live somewhere. So it's not as though current can simply disappear because charge is conserved. This ambiguity in picking your surface ends up not mattering for the application of Ampere's law. That's why we didn't spend a lot of time on it, because this is kind of a theoretical academic conundrum that turns out doesn't really matter. But we are actually going to come back to this in a little bit today, because it's actually consideration of this that leads to one additional law of physics that you haven't, you didn't know yet. So we'll come back to that in a bit. So let me pause a little bit here. So we had these three equations, or really 2 laws of physics. So we have Gauss's law. Both of these are called Gauss's laws. And we have, I need enough space here. We have Ampere's law. And I don't know if you guys remember the introduction to Faraday's law. I told you guys that once you know this much of electricity and magnetism, it's like a puzzle piece that's 80% complete. You can begin to see the pieces that you don't have, not just the pieces that you have from experiment, but pieces that you think you should have, but it's apparent from what you already have that it's missing. That so when you're doing puzzle, it's like there are pieces that you don't even know that you are missing, and there are pieces that you know are missing because you need those pieces to complete a particular area of the puzzle. So Ampere's law was introduced as one of those missing areas, and what I told you then was that there's another missing area here. So, and as a reminder, what has helped us reveal these missing areas is looking for consistency with existing laws of nature. So, once again, this is something that we have gone over before, but it's worth saying again. The way you can see that Faraday's law is missing is that we have such a thing as a motional EMF, or motion-induced voltage. So that's the thing that comes from the Lorentz force law, the electromagnetic force is charge times V, let me write this in a proper way. Charge times electric field plus V cross B. Right? This is the Lorentz force, or the force on an electric charge due to electric and magnetic field. And the specific example that we looked at was the example of solenoid that's moving in the field of in a magnetic field. If I have this magnetic field, and in the demo that you saw that when this solenoid moves, then there's a voltage induced in it, and we can explain that using this electromagnetic force. But what we could not quite explain then without introducing additional law of physics is what happens if it's the magnet that's instead moving. Right? And experimentally, you see the same voltage induced. And just from theoretical consideration, it should make sense to you that it should not make a difference whether it's the loop that's moving or if it's the magnet that's moving, because of what's called the principle of relativity. Laws of physics are the same in any inertial reference frame you are in. So whether you are in a reference frame where the magnet moves, or you are in the reference frame of the magnet and it's the loop that's moving, the end result, the charge is moving, should be the same. And if it's the loop moving, then you are fine. This gives you the induced electric field, or what looks like a kind of analogous to electric field, and you can explain movement of charges based on that. But what you could not explain was when magnet moves, then the only thing happening is that magnetic field is changing, but there's nothing that has the velocity in the solenoid here. So this is the place where you have an internal contradiction. Your theory is incomplete. Two things that should result in the same picture do not say that they result in the same picture. So this is where you have to begin to introduce new laws of physics so that those two pictures agree. And Faraday's law is really the first of these laws that are introduced to enforce a consistency within laws of electricity and magnetism. So let me do it in different color. So this was Faraday's law as we introduced. So you have some quantity that's analogous to voltage, induced electric field times the line integral of electric field around the closed loop. And this is actually new kind of quantity, because until so far, as I was writing this down, I said if you did this, you would get zero. Because electric field, it's a conservative force, so it's path independent. When you go around in a loop, when you do this, you get zero. But what we are now saying is that, well, it's not always zero. You can come up with the situations where it's not zero. And that exact situation is where the magnetic field is changing, in the situation where the magnet is moving. So in that case, you would get this. This is equal to minus, this is the minus sign that we introduced an entire law to explain this minus sign, Lenz's law, times the rate of change of magnetic flux. So that's why sometimes I say electrostatics and magnetostatics. So because we are limiting ourselves to where the charges were not function of time, charges weren't moving around, and then later we are limiting us to where the currents are not a function of time. So now, in this situation, we are removing all those restrictions. We are saying the charge might be a function of time, current might be a function of time, magnetic field might be a function of time. That opens up the possibility that magnetic flux is a function of time. So this derivative may not be zero. Then you get this. And this is Faraday's law. And this was the subject of your exam 3. And in case, it's been a while, so you might have forgotten how it was introduced. But the way I like to introduce, I don't think your textbook does it that way. Because, frankly, this is an experimental law. I'm pretty sure that's how Faraday originally discovered it. But I'm saying if you are more theoretically inclined, you could have actually guessed at it by enforcing a type of consistency with motion-induced voltage that you have seen and you can guess theoretically. So this is the first of the two missing pieces that you can get based on the laws of electromagnetism that you already know. And what we are going to spend the rest of today talking about is this last piece. So this is so it turns out the Ampere's law, as you know it, is incomplete. It's half of Ampere's law. There's one more term there that no one noticed it until a guy named James Clerk Maxwell thought that should be there. That's why we call this entire set of equations, we call this Maxwell's equations. And it's not because Maxwell came up with all of them. He didn't. He didn't come up with any single one of these equations. But he was the guy who came up with what's called Maxwell term. It's the very last term to be discovered, to be reasoned through in electricity and magnetism. And since this is the piece that completes electricity and magnetism, he gets to put his stamp on it. It's sort of, doesn't matter if you're the first to discover. It matters if you are the, first discoverer of the last correct form. So we call this a set of 4 equations, of Maxwell's equations, and this is the Maxwell term, and that will be the important term for what we are going to talk about today. Really, electromagnetic waves. So we need a particular physical situation to consider. That's similar to this physical situation that we are considering. Because when you are looking for these missing pieces of laws of nature, they are not evident in every single situation. Like this Faraday's law, you could have done a bunch of electrostatic and magnetostatic questions and never come across Faraday's law situation. It's only when you consider this particular setup of is the coil moving or is the magnet moving that you start thinking about, oh, I have a law of nature that's missing. So with the Maxwell term, this is the physical situation that Maxwell considered that allowed people to, or allowed Maxwell to realize that there is a missing term in our laws of nature. So you have a current flowing, and this ambiguity in the surface that you can define, that's actually important. Now let me make a small, but before we said this ambiguity doesn't matter because the current enclosed is the same either way, right? Now let me make one tiny modification that will make that ambiguity important again. So what I'm going to do is I have a long wire that's going through like this. And I see that to introduce a contradiction, introduce some kind of self-inconsistency, what I need to do is I need to make the current through this surface different from current through this surface, right? I need to have some current coming in and not leaving through this surface here. And I cannot really have current leaving through any of the side surfaces either. Because if I did that, then they would have net zero current. All right, so using what you know about circuits, this is now something you can do. You can imagine this current being kind of stopped by a capacitor. So instead of a wire connecting through, if you imagine a capacitor being introduced here, so this is kind of a large gap capacitor, but imagine it's a capacitor. Then now you see that this current that's coming in, it's not jumping across the capacitor gap. It's getting stored here as positive charge, right? As that happens, now, if we are looking at it on this other side, then there is actually current flowing here. right? The capacitor doesn't actually stop the current. But the way the current that flows out here happens is you have an accumulation of negative charge on this plate. But this is something you can say. When you are looking at in the in-between region, I guess purple is the only color. When you are looking in the in-between region, there's no current here. No charge ever jumps across the gap. You have positive charge that comes in here, which attracts a negative charge. So that means negative charges are flowing this way. That looks like a positive charge, a positive current flowing the other way. But this is something we can say. There's no current that's actually jumping across this gap. So now we have introduced the internal contradiction. Because when you look at current enclosed through the blue surface, then, so current enclosed through blue surface is the current that was coming in. Let me call that I naught. That's I naught, because it pokes through and it never leaves through any of the side surfaces. So that is my current enclosed. But when you look at the current enclosed through the green surface, then, well, no charge ever crossed this surface. So this is now 0. Yep. So this is an ambiguity that now matters. So you are trying to calculate magnetic field at this point, for example. And if you pick to your, this is the Amperian loop that you picked. And if you had for whatever reason, if you pick the blue surface as the surface that's being enclosed by your Amperian loop, then you would have gotten this answer as your enclosed current. On the other hand, if you went in with a simple surface of the circular surface, then you would have gotten my enclosed current is 0. Now you have two different answers. I guess they can both be wrong, but at least one of them must be wrong. So, at this point in space, you are going to have some kind of magnetic field as a function of position at that point in space. Will this magnetic field be consistent with calculation given through this number or calculation given through this number? Or which one of the two do you think is more likely to be wrong? Like this seems wrong, right? It seems to suggest that there's an abrupt change introduced by just this capacitor being there. But hopefully, intuitively, you think, if I have a current of wire, and if I suddenly replace some part of it with the capacitor, that actually doesn't change anything other than what's going on with the capacitor. So, yeah, so we start out with that intuition that somehow, even though it's not supported by current Ampere's law, that the result that's going to be obtained with this is still the correct result. So now what we do is, by saying that this is the correct result, we are saying that somehow this form of Ampere's law is lacking. It's missing a term. And now we are going to try to guess at what this term must be, so that if we calculate the magnetic field using this, we would get the same answer. But now this is the challenge. We want to think locally. We want to think, what can I calculate using only the quantities that are available along in this circular area? So, this blue area, that's kind of remote. It's more global. I need to reach out to some space that I may not have access to. So now what I want to do is I want to come up with a set of terms so that I can use only the information that's in this surface and still come up with the same result. So my current enclosed will still be 0. But what I need to do is I need to come up with some other quantity that I can say is analogous to the current. Sort of like how the magnetic field can produce a quantity that's analogous to electric field, the induced electric field. So the quantity that we are going to come up with here, that's the quantity that is called displacement current. And I'll just have to tell you that it's an old-fashioned term. So the only sense in which this is like a current is that this is the quantity that's going to be replacing the I enclosed. But when we actually write it down, you will see that in it has nothing to do with the charges moving, at least not literally through. But it's going to be some quantity that will still be associated with this current flowing in. So I guess what I want you to consider is what kind of effect does this current have that you can measure with only the sensors that are placed in along this surface. Like imagine that you have access to nothing else. You simply know two things. You know that there's current coming in here, and you know there's something you can measure here that'll let you figure out what this current is. What kind of things can you measure here? Other than magnetic field, since that's kind of circular reasoning. We're trying to get at an expression for magnetic field. So what can you measure here that tells you that there's something going on with the capacitor? Chris? Yeah, there's going to be electric field. So when this capacitor wasn't charged up at all, with no charge on it, if you measure the electric field in between the capacitor, you would have gotten zero charge, right? As the current comes in, you would have charges accumulating on the capacitor, positive and negative, and you still don't, from here, you don't actually have access to the charges. But what you do have access to is the electric field that those charges are going to be generating. So let me write down E to make sure it's electric field, it's not current. So as more current comes in, there'll be more charges accumulating, and there will be more electric field generated. So Chris, help us clarify this. Is it the electric field itself that tells you that there's current, or something else that's associated with the electric field? Like if you are sitting between the capacitors and you measure the electric field, would you, based on that alone, say there's current coming in, or would you need to see something else?
Oh, it's based on more charge, right? Charges on the plate. So that can either help the current going.
Yeah, so if you had the charges accumulated on the capacitor, then you would already accumulate it. Then with no current coming in, you would have electric field, right? So what do you need to be able to say about the electric field to say that there's current coming in? Yeah, that it's changing. That in this case, the electric field is increasing. But what's going to be important here is, okay, it'll be no current, but as current flows in, there will be a change of electric field. And this is going to be the basis of what we call displacement current. We have to assemble the quantities in a way so that it has correct units and everything. So I guess I'm going to describe what I'll do as a brainstorm or stream of consciousness, because this is what I have so far. I know where I want to get to. I want to have some quantity that will lead me to say this I enclosed being zero doesn't matter. It's as if it's the same current that's coming in. And I know this current is related to this change of electric field. But I have no formula that's giving me that direct connection. So I don't know if you guys have done any stream of consciousness writing. I'm just going to start from one point. And I'm just going to write down all the relationships I know, hoping that from this starting point, I will somehow be able to get to this end point that contains a term with this. and all the other coefficients that I need with it. So let me just start that as some kind of stream of consciousness or brainstorm. I don't know what the correct term would be. So, ideally, this is something that you could do with a lot more time in group setting, but I don't really have that time. So let me just speed through it. So I'm just going to start out with a current. Current is something that I know. That's the place I would start from. So when you do something like this, sometimes you might want to go backwards, like start from the end point and go the other way. But my preference almost always to go in the forward direction. It's only when you get stuck that you enlist to consider backward direction. This is, by the way, the same with any kind of mathematical proofs you might do. So I start out with the current. So I have current I naught coming in. What is this current? What else is this current related to that I can write down some equations for? Chris? Okay, current is related to V over R. Now, in this setup, is there any register anywhere? So yeah, there's no register, so this relationship is there. I might write it down as I'm brainstorming, but it probably won't get me to where I want. But you can write it down, and it's the whole idea of brainstorm. Not everything you write down has to be correct, but hopefully. So as you're doing this, you have to critically think for yourself. Does this relate to my end goal? And when you recognize it doesn't, label it as dead end and try something else. Anything else?
It's also the rate of change of charge over time.
Yeah, so that's the other relationship, right? When you have capacitor, the amount of current coming in is related to rate of change of the charge on the capacitor that you had when you are dealing with the circuit. So this current is the rate of change of the amount of charge on the capacitor. All right, so I can go from current to charge on the capacitor. Now, I guess what I want expressed, so I see that this is going somewhere because it's having to do with the capacitor. Now, is there a way this directly relates to electric field? Charge on capacitor with the electric field. Does anyone remember the formulas? This is where a good knowledge of, this is why I keep telling you to memorize formulas. When you're doing brainstorm like this, it's a lot easier if you don't also have to look through your formulas. If you can just scroll through what's already in your head. So let me, speed through this portion. I'll just write down the formulas that I do have memorized. These are the set of formulas that were useful for dealing with a capacitor. If I have parallel plate capacitor setup, or more precisely, it's a parallel infinite plane of charged particles. I have charge density of plus sigma on one, minus sigma on the other. Then with this setup, do people remember what the electric field between those two were? Yes? No?
Is it sigma over permeability through space?
Permittivity of, yeah, sigma over epsilon naught. Sigma over, I prefer to call it electric constant because permittivity, permeability, who knows what they mean. But you do know that epsilon naught has to do with electricity. Okay? So this is the formula that hopefully you have memorized. This is the electric field in between parallel plate capacitor. Yeah. Once you remember this much, then now you recognize that the sigma has something to do with the charge. That's the charge density, Q over A. So we started out by saying it's an infinite plate capacitor, but in a real capacitor, it's going to have some finite area A. So let me rewrite this electric field as Q over A over epsilon naught. All right, it seems like I can actually rewrite this. So let me rewrite it this way. So I'm going to take this expression, electric field magnitude is equal to this right-hand side, and solve this for Q. I can say Q is equal to area times E, or area times epsilon naught times E. All right, so epsilon naught times area times E. Okay. All right, so continuing with this line of thought, I can take this, plug it in here, and see what happens. When I take this and plug it in here, I get rate of change of time, rate of change with respect to time of epsilon naught A electric field magnitude. Epsilon naught is a constant, right? That's a electric constant. Area, it's a constant, right? Now, what is it area of? Because this is a common situation that people get into where you have more than one variable representing a type of quantity and you get them mixed up. People do that every single time with the E over M experiment that a lot of you did. You have more than one circle, so you get radius for one circle mixed up with the radius for other circle. So here I want to be careful. Which area are we talking about? Are we talking about these areas that are being defined by Amperian loop? Or is it some other area? I see that I have drawn it confusingly. Let me draw my capacitor a little bit smaller so that you can see the cross-sectional area of a capacitor, which might be represented by this, is significantly smaller than the Amperian loop area. Which area are we talking about? Yeah, this area, cross-sectional area of the capacitor, right? Because that was the sense in which we are using A every single time. It's a charge on capacitor over area of the capacitor. So here, this is still area of the capacitor. So I guess nothing actually stops us from writing it down this way. We could write it down this way. Epsilon naught A times d dt. Epsilon naught A times d dt. But I'm kind of looking forward or backward to how this expression is written. And when I write this down, I want it to have some kind of similarity to some stuff I already have. So this, remember the definition of magnetic flux. Magnetic flux was magnetic field times the area. I mean, if you are being picky about it, this is actually the dot product between the two vector quantities. And if you are being really picky about it, then it's actually, if magnetic field is uniform, then you have to imagine integrating it. So there are all those refinements that you might want to worry about depending on the problem. But at the very basic level, magnetic flux is magnetic field times area. So we want to do the same thing here and express area times electric field as the electric flux. So say that this is the quantity that we are going to define as the electric flux. It's not like this is the first time you are seeing electric flux. This is also electric flux. Except every time this came up, I kept saying, I don't care about electric flux. Apparently you do, depending on the situation. So with that symbol, this is how we would write down the final version of this line of expressions. Starting from this I naught, we would say, well, this relates to the charge on the capacitor, which relates to the electric field, which leads to this final relationship. So epsilon naught is still constant. Let me pull it out. Epsilon naught times rate of change of the electric flux. So this is where you end up. That if you have certain amount of current coming into the capacitor, you can say that that is going to be related to how much the electric flux through this area is changing. And actually, I say electric flux through this area, but it's electric flux through this entire area, since outside this electric field is 0. So when you imagine doing that whole area integral, that reduces down to E times this area in the end, anyway, when you do it properly. Okay? So this is what we are going to call displacement current. This is the quantity that we are going to end up calling displacement current. And this is probably a good place to ask this question. In what sense is that like a current? In what sense is the rate of change of electric flux like a current? Is there a movement of charge involved through this surface? Through this surface? No, I mean, there has to be movement of some charge elsewhere for the electric field to be changing, right? But when you're looking locally here, there's no charge that's moving across here. So in what sense is this quantity, which is, the name for this quantity is displacement current. So it must have something to do with, well, I guess these words must mean something. The word current must mean something. The word displacement, that's actually a harder one to explain. It's an old-fashioned term. Yes?
Is it because it modifies the current side of the Ampere's law?
That's really the biggest reason. This is the quantity that we are going to pretend is something that acts like a current here. It's going to enter into here. So the modified version of Ampere's law will look like this. If this additional term, it will have this coefficient of mu naught, just like the other term. It will be mu naught times displacement current. So the sense in which this is like a current is sort of similar sense in which V cross B was like an electric field. You see that here they are being added together, and I would not add them together unless they are like each other in some sense. And here, I guess, if you had to go one step further, you could say this is like a current in the same sense that current can generate magnetic field, and this also generates magnetic field, the same way current does. But beyond that, what this quantity is, well, it's a rate of change of electric field. And I think the phrase displacement is a little bit, I don't actually know the history of the term. What I do know from upper division electrodynamics is that there's a quantity called the displacement field. The displacement field was defined as epsilon naught times E. If it's in vacuum, this would be epsilon naught. If it's in matter, then this would be the permittivity of the material. So this is the quantity called the displacement field in upper division electrodynamics. And I'm pretty sure that term displacement comes from this term displacement. And if I had to stretch and guess why is this called displacement, I would guess that has something to do with the separation of charge. Maybe, I don't know. But really what I want you to take away is that this acts like a current in the sense that it generates magnetic field. Exactly the same way current does. And we express that here with the modification of Ampere's law. We have this one additional term to Ampere's law now. Instead of simply saying magnetic field is, this line integral of magnetic field is mu naught I enclosed, we say it's, well, that plus mu naught times that epsilon naught, the electric flux, or rate of change of electric flux. This is the term we call Maxwell term, and this is the last term of Maxwell's equations. With this, these four equations are combined, are called Maxwell's equation, and this is it's a representation, statement of our complete understanding of electromagnetism. And when you pause a little bit and look at it, you can see how much story this is telling. I don't know, have I said in this class that the theory of electricity and magnetism is the first complete law of nature, complete theory of nature that we have? Well, it is. So, everything else that you have learned so far before electricity and magnetism, it's all bits and pieces. So you had Newton's law of motion, but it simply relates to force to acceleration. It doesn't say anything other than that. It doesn't tell you where the force is coming from. It doesn't, so force can be spring force, it can be gravity, it can be electric force. So Newton's law of motion is not complete theory of physics. It's a tool to be used in analyzing other theories of physics. There's Newton's law of universal gravitation, and I guess in some sense you could say that is a complete theory of physics, in the sense that up until early 20th century we didn't know what else it connected to. But theory of gravity is it's a boring theory. It doesn't really say it doesn't say anything other than inverse square law. You stop there. There's nothing more interesting to say about gravity after that. The thing about gravitational wave that you might have heard about, that was, actually it's a Nobel Prize this year, right? Or was it last year? But that actually comes out of Einstein's theory of general relativity. So that comes actually after this. So this is the first interesting set of theory of physics that says everything there is to say about a particular aspect of nature. So here we are limiting ourselves to things that have something to do with electricity or magnetism. If it has nothing to do with electricity and magnetism, then this doesn't really tell us anything. The nuclear forces, this doesn't say anything. But surprising number of things are about electricity and magnetism. All the intermolecular forces, that explains why my hand doesn't go through the other hand. That's actually electric force at its very basic nature. All the things that are binding molecules together, it's electric in its very basic nature. So electricity and magnetism, it includes a lot. And this theory tells you everything there is to know. You might say the rest is filling in the details. And as you'll learn in Physics 4C, those details actually can get complicated. But this is still correct as far as we know. Even when you include quantum mechanics, even when you include the special relativity, nothing that I wrote down here needs to change. This, if you are doing graduate physics, graduate school physics, this is still the place you would start from. Oh, except you would use the differential form that I'm going to write down shortly. So that's the sense, this is the first complete theory of physics. And this is really the story I want you to take a little breather and notice what it's saying. So let's just go back through history quickly. We started out by saying that electric field is generated by charges. Not that new. It's starting to get a little bit abstract, talking about fields and whatnot. But all right, that seems reasonable. And when the same time we introduced the idea of field, we connect the field to force this way, right? So electricity, simple, whatever. And then we start talking about magnetic field. And magnetism, we did talk about it, but your intuition about magnetism has more to do with magnetic interaction between a permanent magnet and a ferromagnetic object, or between two permanent magnets. And when you look at magnetism that way, it's completely disconnected from electricity. There's nothing that looks electric here, right? And you might look at something like this demo that you saw a while ago. This demo of a magnet falling through a conducting material somehow a lot more slowly than otherwise. And that looks weird, but I guess this is not completely magnetic. But just looking at it, you wouldn't guess the immediate connection to the electricity. So really the modern electromagnetism, it starts out by highlighting the connection between magnetism and electricity. So here, Ampere's law actually starts off with that. It says that the magnetic field is generated by current, or charges moving. And about the same time we were introducing this, we introduced this. Because of apparent lack of magnetic monopole, we have to say any kind of force due to magnetic field is actually force on a moving charge. So you need to have electric charge and you need to have velocity. So starting with Ampere's law, you are starting to build a connection between electricity and magnetism by saying a moving charge can produce magnetic field. Yeah? And I guess this is the place where you might begin to wonder if the relationship is reciprocal. As in, if a moving charge could produce magnetic field, then could a moving magnetic charge produce electric field? Well, there's no such a thing as a magnetic charge, but there are permanent magnets that do generate magnetic field. And when these permanent magnets move, they do generate electric field. And that's what you are seeing here. But because of a lack of magnetic charge, this has to be stated in a bit of a roundabout way. Instead of saying that magnetic current is generating electric field, we are saying, well, not magnetic current because that doesn't exist, but the change of magnetic flux or change of magnetic field is what's generating electric field. And when you say it that way, this is one more question that someone who has too much or just the right amount of time to think about this might ask. If a changing magnetic field can generate electric field, can the reverse happen? Can a changing electric field generate magnetic field? And up until this point, your answer was no. Your electric field could be changing. Now, if you mean by changing electric field, you mean current, then sure, there it is. But this is what's saying, yes, changing electric field will generate magnetic field. So the entirety of Maxwell's equation relationship is this back and forth. What is the connection between the electricity and magnetism? And this is the one that closes the loop. This is the last set of relationships that says that what happens from magnetism to electricity also happens in reverse. It happens from electric field to magnetic field. And any sort of lack of symmetry between these two, it really comes down to the fact that there is no magnetic monopole. If there had been magnetic charge, then this would look something like this. Like this would be something like a mu naught times magnetic charge enclosed, right? And here it would look something like, I have to get the units right. Let's see. I don't think I got this unit right either. Okay, let me stop here. I try this every semester and I haven't worked out the units ahead of time. So, but you would introduce terms that depend on that missing magnetic charge. There will be one depending on magnetic charge here, and there will be one depending on magnetic current here. So, any asymmetry you see here now is from that asymmetry that magnetic charges, for whatever reason, just doesn't exist. And that's why there are people still looking for magnetic monopoles. If somebody ever finds it, they'll win Nobel Prize probably based on that. Because people have been looking for it for a long time. There are theories that says why it might not exist or why might they be really rare, like one in an entire galaxy. And but there are ready-made. So one of the questions in modern physics is something called the quantization of charge. Why is electric charge? Why does it come in that unit that we see, charge of electron? And you can actually explain that once you suppose that there's at least one magnetic monopole. Then there's some quantum mechanical feature that you have to make consistent, and that'll explain it. But for the purpose of this class, we'll just end here that there are no magnetic monopoles, but there's no good reason that they shouldn't exist. So this is Maxwell's equations. It's the complete statement of electricity and magnetism. And now having spent all this time, we won't really do much with it. We will do exactly one thing with it. And this is the one thing that we needed this Maxwell term to do. It's to describe something called electromagnetic wave. It's the question of what happens if I have a charge that's in space and it's oscillating up and down. If I have that, what kind of effect would this produce in the space around it? And before we had this term, what we could do was kind of limited. So, if I have an electric charge in space, it's going to produce electric field, right? Yes? Sort of radially going upward. And as this moves, the electric field will change. Big deal, nothing surprising. All right, so we had that from Gauss's law. And you could also describe a charge moving up and down as a current. Kind of something analogous to current, right? Current moving up and current moving down. So you could say, oh, that's a current. So based on Ampere's law, we could say that generates magnetic field that's going around the loop like this. And as this moves up and down, current is changing, maybe sinusoidally. That changes the magnetic field, maybe sinusoidally. And you could say even up to this much. You could say that changing magnetic field will now generate electric field. So this is the picture I was looking up just before class. So this is the picture that you could have gotten so far. You could have said with a charge moving up and down, that generates magnetic field going around in a loop like this. And based on this magnetic field changing, you could say that generates this electric field going like this, right? And that would be where we stop. Without Maxwell term, so I have a changing electric field, but without the Maxwell term, the changing electric field doesn't do anything. So we would say, all right, that's where we stop. No more interesting features. All these things go down as 1 over r squared, and end of story. With this term, what changes is that this chain of events continue. And this results in something called radiated field. And these electric fields that are generated this way, they don't go down as 1 over r squared. They go down as 1 over r. So the electric field strength actually, so we'll just stop there because we're going to talk about plane wave where we're going to pretend that they don't change at all. But so this chain of events starting with here now becomes possible because of Maxwell term. Because of Maxwell term, this changing electric field can produce this changing magnetic field, which can now produce this changing electric field, and then this goes on forever. And this is what we refer to as electromagnetic wave. And I think I might have just enough time. I have about 20 minutes to kind of demonstrate that we do have the correct mathematical relationship to suppose that something like this actually happens. So let me set that up. So this is our Maxwell's equation. I'm going to simplify our Maxwell's equation a little bit, but let me start from, so your textbook tries to do it using this integral form of Maxwell's equations. So you can look at the textbook for that. I'm going to use the differential form because it's a lot easier. And when you do any kind of serious proof work, that's what people would use anyway. It's in this lower division class where some students may not have taken multivariable calculus that your textbook is forced to use this integral formulation, but what's more natural to use is it's the derivative formulation. So let me write that down first. So differential form of Maxwell's equation. I will write them down in the same order so that you can draw some kind of relationship between them. Gauss's law says this: the divergence of electric field is equal to the charge density. So, with all this differential form, one thing that you should remember is that they are local. As in, when you describe electric field at a point, so you are dealing with the derivatives at the point, so you are dealing with the charge density at the point. You get this, enclosed charge, enclosed current, all this stuff when you integrate over some volume or integrate over some area. So it's going to be charge density divided by epsilon naught. And divergence of magnetic field corresponding to this is 0 because there's no magnetic charge. And the one corresponding to this is the curl. Curl of magnetic field is, let me write this down including the Maxwell's term. So let me factor out mu naught. It's mu naught times current enclosed will become current density. So let me use the standard symbol J for that. So just as a reminder, the current density J is equal to current divided by area, and I guess the vector thing is in the normal direction. Okay? So that's the current density. Plus, we need this displacement current, except I'm dividing out area anyway. So this is going to be epsilon naught, rate of change of electric field. And I can leave the vector term as it is. I'll talk about divergence and curl. And the last thing is the curl of electric field. Curl of electric field is given by the differential version of this, which means I get rid of the area. So it'll be minus rate of change of magnetic field. So this is the differential form of Maxwell's equations. And because of the prerequisite / co-requisite arrangement for this class, I have to ask, how many people here are not currently taking or have not already taken Math 3C? Okay, so for those of you who have not taken Math 3C, these symbols don't quite mean much. So let me explain this. So the three symbols I need to introduce are these. One is what's called gradient operator. And I mean, operator sounds fancy, but like a derivative is an operator. It's a differential operator. And gradient operator is the derivative in 3 dimensions. So let me just write down the symbol. It's represented by this upside down triangle with a little vector thing on top. It's because it's a vector operator. Let me write down its form in the Cartesian coordinates. In Cartesian coordinates, this is, so it has 3 components, x hat, y hat, z hat. So it has x hat component, y hat component, plus z hat component. And each of these components are the derivative operator, the partial derivative. So component here is derivative with respect to x. Component here is derivative with respect to y. Component here is derivative with respect to z. I guess the one funny thing about operator is that this is not a function. This only becomes meaningful when you act on a function with it. This is like a reminder, I am going to take a derivative of what? Whatever function comes after this. Yeah, so that's something your math class would spend more proper amount of time. I'll just leave that there. So with this gradient operator, your calculus class would define 2 particular types of operation. Or let me write down all 3. So I mean, so you have the gradient. So gradient is the simple one. It's simply this acting on a function. So a gradient of, let's say, you have a scalar function of position x, y, z. So this could be a function of temperature, right? Temperature is scalar, and you can express it as a function of 3-dimensional coordinate system. So when you take a gradient, then this is the what's called a gradient of that function. And it gives you a vector quantity. So like when you think about temperature gradient has a sense of how quickly it's changing as a function of distance and in what direction it's changing. Good? So this is the one operation you can define with this. And the other two operations are, I will write it down, and I'll tell you that mathematically it's not that complicated from something that you already know, but this is something your Math 3C will spend a lot of time trying to build the intuition for, that I don't have time for. So let me first write it down. The two operations that are defined are what's called divergence and curl. It's two particular type of vector operations you can do with this vector operator. Think of it like this is like a scalar multiplication. You are multiplying a vector to a scalar, you get a vector quantity, right? So in both of these, I'm going to multiply a vector with a vector. Divergence is where I get a scalar. Curl is where I get another vector. So divergence, does this all sound familiar? Like with the vector operations? What kind of vector operation did you do where you got a scalar? Dot product, right? Yeah, so that's what divergence is. It's a dot product. It looks like a dot product. I mean, there's a little bit of, it looks like a dot product. So it's the gradient operator, dot product, with some kind of a vector field. So, some kind of vector field. So I didn't write down vector field here, so let me write it down here. A vector field A, for example, would be, it's a functional position, x, y, z, and possibly time. And it'll have a component. It'll have x component, it'll have y component, and it'll have z component. Do you know anything that's like this vector field? Any physical quantity that can be expressed as a vector field?
Electric field?
Yeah. Electric field and magnetic fields are examples of vector fields. It's vector quantity that's a function of position, has three components. So this looks like a dot product between two vectors. And when you write it out, it's exactly what that is. When you write it out, let me write it out in Cartesian coordinates so that you can see that it's nothing scary. This dot product, it becomes this. So, it's only the x dot x that doesn't disappear. So when you do this dot product, there's technically like 9 different products, right? Between 3 of these components and 3 of this component. Of those 9, only 3 survive. X dot x, y dot y, and z dot z. The rest go to 0. So you end up with the x derivative of ax plus the y derivative of ay plus the z derivative of az. In the Cartesian coordinate system, all this looks pretty nice. Something that your Math 3C would spend a lot of time going over is how to do this in different coordinate systems, like a cylindrical and spherical. Those look nasty, and I will not deal with that in this class because I don't have the formulas memorized for once. So that's a divergence. Curl is the quantity that gives you a vector thing back. And if you remember, the product that gave you a vector back was cross product, right? And so this is going to look like this. It's going to look like a cross product. It'll look like this vector operator cross product with the other vector. The only thing that you have to be careful with in this is the order of operation. Not, in the sense of this versus the other way around. Like, A cross delta, this means nothing. Like, this is not curl. Because this is one thing you have to watch out for operators. They have to be coming right in front of something that it's acting on. When you swap the order, you get something entirely different. It's still an operator. It doesn't act on anything. So when you write down this curl operation, you have to be careful in keeping that order same. When you write it down, the derivative always has to come before the component. Yeah? So this is probably where it's worth. Do people here remember the component representation of cross product? Yes, no? Let me give you a shortcut to memorize it. How many of you have taken Math 3E, linear algebra matrices? Okay, enough of you. When you take, how many here have heard of determinant? I feel like one determinant part of pre-calculus. Like there's a little bit of matrix in the college algebra, and there you talk about determinants, right? Okay, yeah. So this is based on determinant. This is how you can memorize cross product A cross B. And this is really the simplest way to memorize a cross product. You say that A cross B. So A would have, so A has component AX, AY, AZ. And B has component BX, BY, BZ. And this A cross B can be represented this way. The quickest way to write down the component representation is to say this is equal to kind of a fake determinant. Determinant of this made up 3 by 3 matrix that looks kind of odd. It's, you say it's the determinant of this 3 by 3 matrix that looks like the first row is the unit vectors, x hat, y hat, z hat. The second row is the first vector, ax, ay, az. The last third row is the second vector, components of the second vector, bx, by, bz. How many people here remember the shortcut for calculating the determinant of a 3 by 3 matrix? Works only for 3 by 3 matrix, doesn't work for anything else. No? Yeah, well, I'm almost out of time, so let me wrap up this portion. So the first thing you do is you copy over these two columns so that it looks like a column 1, 2, 3, and then you start repeating column 1, 2 again. It's a graphical method, so you need to have this as well. You need these auxiliary figures to help you make the next figure. So you group these terms together this way. So each of your term is going to be product of 3 symbols. And those 3 symbols are formed this way. You go down diagonally. You can go down to the right. That'll give you these 3 groupings. This is the diagonal grouping of 1, 2, 3 groupings. Okay? And with each of these groupings, you associate a positive sign. That's one set of terms you have in the cross product. If you have seen cross product, it looks complicated, right? So these 3 won't be enough. There's 3 more. And those other 3 you get from diagonal going down to the left. So you have, so these are the 3 diagonal groupings going down to the left. And with these terms, you associate a minus sign. So there's going to be a total of 6 terms. It's usually grouped together by their like terms and unit vectors. So let me write them down that way. And let me write them down that way. And that'll be the starting place for talking about electromagnetic waves when we come back in the lab section to wrap up this discussion. So, so it'll be long, so let me write it down carefully. I'm going to write down a group of 2 terms for the x, 2 terms containing the unit vector x hat, and 2 terms containing unit vector y hat, and another 2 terms containing unit vector z hat. And I'll just hunt and pack those ones. So I have, so this is x hat. So one of the terms must be ay and bz. That has plus sign with it. So x hat, so plus ay bz. And let me go looking for, here's x hat. So another term must have az and by with a minus sign in front. Minus az by. And this is where I'm going to be super careful. I'm always going to write down a before b. It's because I'm looking forward to this, where I need to always write down the derivative before the thing I'm differentiating. I can never swap that order. So, I mean, yeah, so, all right. So y hat, let me go more quickly. az and bx, az, bx, that's the positive sign. Y hat here, ax, bz, that's minus sign. Minus ax, bz. And the last term, ax, by, minus ay, bx. And there is actually a pattern to this, something called the cyclical versus anti-cyclical permutation that you can actually use that to memorize. But this is the quickest way that depends on something that you are supposed to know already. So let me write this down, and we'll wrap up there. So, the curl is essentially cross product of this vector and this vector. And as I write down, I'm going to refer to that thing that I just built up, so that I can say curl is, all right, the y component of the first, or I'm looking at the x component of the result of the curl first. And for that x component, I look at the y component of first vector. So the derivative with respect to y, and the g component of the second vector, so derivative with respect to, I guess, y of the g component of the a, so a sub g, minus g component, derivative with respect to g, of the y component of a function. You see there's a lot of moving parts that you need to keep them separate. You cannot get different components mixed in, because there's 3 different components to keep track of. Y component of the curl would be, all right, g component, so the derivative with respect to g, of x component, so a sub x, the function, minus the derivative with respect to x of the az function. You might begin to notice some similarities, as in each component happens only once in any term. xyz, xzy, yzx, yxg. And you can use that to make sure you didn't make a mistake. The last term is the g component, this one here. So x component of the first vector, so derivative with respect to x of the y component, so of the function ay, minus derivative with respect to y of the x component ax. So this complicated expression is what's called a curl of a vector field. And the reason I need to introduce this is to tell you about what Maxwell's equation says about curl of magnetic field or electric field.